Step aboard a Japanese Shinkansen, slicing through countryside at 300 kilometers an hour. Inside the cafe car, a barista tilts a silver pitcher. The milk ribbon curls into a rosette with lazy grace, untroubled by the hurtling world beyond the window. No cup skitters, no spoon rattles against porcelain. To every traveler nursing a latte, the carriage feels as hushed as a library. Swap rails for sky. A parabolic flight aircraft, nicknamed the Vomit Comet, arcs downward, and the cabin dissolves into weightlessness. Pens float, laughter bubbles, yet a camera fixed to a seat frame sees everyone drift in slow ballet. Unaware that the aircraft itself is plunging earthward at hundreds of kilometers per hour. Now ascend to the International Space Station? Uncapped droplets coalesce. Coffee orbs glide from pouch to lips, and astronauts perform somersaults with fingertip pushes. The station circles Earth every 90 minutes, but inside, only the view through a hatch window betrays the speed. Each scene, train, plane, orbital lab, confirms a profound principle. Within a cabin moving at constant velocity, no purely internal experiment can reveal the motion. Whether you trace pendulums, pour beverages, or toss keys, the outcomes mirror those in any quiet room ashore. The universe, it seems, grants no badge for steady travel. Uniform motion is indistinguishable from rest. Inertia, once Newton's radical decree, now whispers a subtler truth. Stillness is not an absolute location, but a shared state of glide, felt only when some outside force dares to disturb the peace. Yet a nagging question lingers. If all straight-line motion is created equal, what about rotation? Spin in your desk chair, and you feel the outward tug. Spin in an empty field at midnight, and the tug persists. Against what exactly are you turning? Enter Ernst Mach, the sharp-eyed 19th century physicist-philosopher. He gazed at Newton's rotating bucket and wondered whether the water's curved surface truly testified to an invisible, absolute space. Suppose, Mach mused, the stars overhead were whisked away. Would the water still climb the bucket walls? Or does its rise depend on a dialogue with that glittering backdrop? Perhaps inertia itself, its self-resistance to spin or shove as a gentle handshake with the distant mass of the universe. The idea is disarming in its simplicity. Motion means nothing unless there is something else to move relative to. Pirouetting ice skater speeds her spin by tucking arms. But the sense of rotation? The outward pull she counteracts might be her body conversing with Andromeda and the Virgo cluster, silent partners across unfathomable gulfs. Mach's principle, as it came to be called, lacked equations, yet seated deep unease in young Albert Einstein. If inertia is woven with cosmic matter, then perhaps gravity and motion are threads of the same fabric. Einstein carried that hunch into his happiest thought, the elevator paradox that would birth general relativity. For now, let Mach's whisper echo. The straight lines and steady spins we take for granted may be votes tallied by every star in the night sky. Our next step is into an elevator, where floors vanish and space itself reveals how profoundly that cosmic quorum shapes the paths we call inertial. Picture yourself in a windowless elevator adrift in deep space. The cabin floats weightless. Your feet hover just above the floor. Now imagine an unseen hand attaching a cable and hauling the car upward with constant acceleration. Instantly, your soles press against the metal, coins fall to the deck, and a dangling keychain points down. From inside, no experiment can tell whether a planet's gravity tugs at you or the cable's steady pull fakes it. In 1907, this simple daydream washed over Albert Einstein like sunrise. The happiest thought of my life, he called it. Gravity and acceleration are locally indistinguishable. Extend that idea, and inertia itself, once a silent companion, becomes the star of the show. A falling apple is not pulled. It is freely tracing the straightest possible line through curved space-time. An unforced geodesic. You, standing on Earth's surface, feel weight precisely because the ground accelerates upward, forever deflecting you from that effortless path. Experiments now enact Einstein's reverie with exquisite precision. Atomic fountains toss clouds of rubidium upward. As the atoms rise and fall, they tick like quantum pendulums, measuring tiny frequency shifts predicted by the equivalence principle. Laser interferometers compare clocks on airplane wings to those on runways, confirming that acceleration and gravity trade roles flawlessly. Thus, inertia is reborn as geometry. The elevator's floor, the Earth's crust, even the bright arc of Mercury's orbit. All are stage props that push against objects, yearning to glide straight on space-time's subtle curves. If space-time itself sets the rails of inertia, can we see those rails twist? Engineers answer with gyroscopes, stalwart guardians of direction. On jetliners, ring laser gyros trap light racing in opposite loops. Any rotation lengthens one path, shortens the other. And the interference whisper tells pilots their true heading, indifferent to clouds or compass errors. Push the concept to cosmic scales, and you find Gravity Probe B, launched in 2004. Inside its dew-cold shell floated for quartz spheres, polished rounder than raindrops. Each sphere spun like a perfect top, its axis pointing at a distant guide star. According to Einstein, Earth's mass-dense space-time, and because our planet also turns, drags space-time around with it in a gentle whirl. After a year of orbit, the probe reported a minute drift, just 39 milliseconds, but exactly the swirl general relativity foretold. The gyroscopes had felt space-time's eddy without touching air, water, or magnetic field. Closer to home, consider a spinning bicycle wheel held by its axle. Tilt the axle and mysterious torques appear, steering it against your hands. Yet those torques vanish inside free-falling parabolic aircraft. The wheel's axis keeps faith with distant quasars, defying the plane's fleeting arcs. Even a child's toy becomes a cosmic compass, once divorced from friction and floorboards. These experiments reveal a universe where rotation is never absolute, yet never free. It references space-time's local twist, which in turn is sculpted by the mass and motion of everything else. Mach's whisper lingers, now spoken through cryogenic tops and loops of captive light. The cosmos is both stage and choreographer, guiding every pirouette by the weight of its own invisible hands. Stand in a quiet desert and point a radio dish at the sky. Bathed in microwave haze, the afterglow of the Big Bang, the instrument hears a faint hiss, only 3 kelvins above absolute zero. Yet that hiss is hotter in one slice of sky and colder in the opposite slice by 1 part in 1,000. The pattern is a dipole, a Doppler blush betraying that Earth. The Sun and the Milky Way surge through the cosmic sea at roughly 370 kilometers per second. Have we then rediscovered Newton's absolute rest? Not quite. The cosmic microwave background offers a practical compass, not a privileged throne. Any observer, anywhere, can subtract the dipole from her maps and call herself at rest with respect to that ancient light. The laws of physics remain unchanged. If she instead rides the galactic wind, only the temperature pattern shifts. Inertia still refuses to pick favorites. It merely notes that the newborn universe left a convenient backdrop against which we can measure our own drift. Zoom closer, and the picture complicates. The local group of galaxies clings together, ignoring the grand expansion because gravity knits it tight. Farther out, space itself stretches, carrying Virgo clusters apart like dots on an inflating balloon. Motion born not of jets or rockets, but of geometry's slow breath. Thus we inhabit nested frames. Bound orbits inside galactic eddies inside a Hubble flow. The whole flow surfing the leftover radiation of the primordial fireball. In this layered hierarchy, inertia is democratic. Straight lines are drawn locally by spacetime, while the cosmic background supplies only a gentle reference grid. A whisper, not a mandate, reminding us how swiftly our seemingly still lives rush through the deep. We have drifted from the silence of a latte on a racing train to microwaves born when atoms did not yet exist. And everywhere the verdict is the same. Motion is context, not command. Neither bucket walls nor ether winds. Not even the newborn light of the cosmos can claim ultimate authority. Instead, straightness and stillness arise from an ever-changing conversation between matter and the pliant fabric that enfolds it. But a subtler story waits in those folds. If space-time can whirl around Earth and swell between galaxies, what paths do free objects truly follow? What shape does inertia take when gravity itself is nothing more or less than geometry in motion? To answer, we must leave anchors behind and accept that the purest expression of Newton's first law is not a line on a grid, but a geodesic. the natural, effort-free trajectory inscribed by space-time's own curvature. In the next part, we will step into that geometric realm. We will ride Einstein's elevator out into interplanetary space. Feel how GPS satellites keep time by tracing geodesics bent by Earth's mass, and watch dark energy begin to tug on the grid itself, lengthening every yardstick in the cosmic loom. So pause, take a breath, and feel the floor beneath you solid, reassuring, yet quietly accelerating upward against your innate desire to fall along an unseen curve. Ahead lies the revelation that inertia, once thought a simple stubbornness, is the universe's way of writing its deepest script. The story of how matter, light, and expanding space choreograph a dance where motion never dies, but simply follows the bends of an ever-unfolding canvas.